This is a video for AQA Discrete Mathematics. This is Binary Operations section 1.2, where we're looking at the idea of Cayley tables. So remember then, with a binary operation we can take some defined operation and perform it on elements from a set. So here's the set of numbers 1, -1, I and negative I, where I of course is the square root of -1. And we're going to consider the multiplication table for that set of 4 elements. And you'll see that when we multiply something by 1, whatever it is, we're going to get the answer which is exactly the same, of course, so negative I at the end. If we multiply by -1, then it's going to turn all those negative, change the sign on them, so this then becomes 1. This one here is going to be negative I, and this one then is plus I, just I. When we multiply by I, and then negative I, and then I squared. Well, I squared is -1, as you well know, and then negative I squared must therefore be negative of -1, which is +1. And finally, multiply by negative I gives us negative I, and then we get plus I, negative of I squared, which is 1, and then finally at the end I squared, which is -1. So those are all the outputs, and notice first of all that those outputs are all elements of our fixed set of 4 things there. That's one thing. You might also look a little bit more closely and you'll see that every single row and every column contains those 4 elements. So this is really what we mean by a Cayley table, and these were first thought of, or at least studied, by a 19th century mathematician, Arthur Cayley, hence their name. So in the Cayley table, it's just a case of putting in the outputs from the elements that are combined by the operation. So the features were then that we had certainly the inputs were all within the set, so it's technically what we call a closed set. However, we don't necessarily have to have associativity, and we don't necessarily need to have commutativity. It's such that in this particular set then it is commutative, so you can see if I combine I and 1 together, then I get the same as combining 1 and I. Or -1 and negative I, so -1 and negative I and negative I and -1 both give I as their combined element. So if it is commutative, it will have some reflective property along this leading diagonal. However, it's not necessarily so. Associativity is also not necessarily going to be true for Cayley tables, but this property was sometimes referred to as a Latin square property, where we've got 1 element in each of the rows and 1 in each of the columns. So, as to construct a Cayley table for the set 0, 1, 2, 3, 4 under modular arithmetic addition, then remember that when we have modular addition we take the remainder after division by 5. So 0 isn't going to make any difference at all, 0, 1, 2, 3, 4, but when we add 1, each of these numbers is going to increase by 1 till we get to 1 plus 4 is 5, so modular addition, that is 0. The next one's increased by 2, so we're adding 2, 2, 3, 4, and then of course 2 plus 3 is 5, which is 0, and then 1. And now you can see what's happening in the next row. Everything's increasing by 3, so that becomes 3, 4, and so modular 5, 0, 1, and 2. and finally 4, and then 0 and 1, 2 and 3. So the Cayley table there, again you can see each element appearing in every row and every column. Well, that's the end of this video on Cayley tables. In the next video we'll be considering the idea of identity and inverses.